Okay, cool. Very nice.
All right, great.
Okay, Malte, so shall we start now, or do you want to wait for a few minutes?
No, it's fine to me. Let's kick it off then. Yeah.
Okay, cool. Then Jen, please mute yourself and let me give a short intro. So basically, welcome everybody. Welcome to the webinar that we co-host with Deepset. So today we are going to talk about neural search, and I hope you all have a wonderful evening with us and enjoy all the knowledge and you know, this open source spirit with us. In the meantime, so we have actually we do have some polling. So at the bottom of the Zoom. So if you are using Zoom, you should see there is a polling where you can basically select where you come from, what is your background, and so on. And regarding the question and answer, right? So please do not use the chat. So there is a chat button on the left-hand side, and there is a QA button on the right-hand side. Please do not use the chat. So I actually disabled it already. Right? So use the QA button, and then you can ask questions, and other people can vote on the question that you ask, and we will answer part of the question in live. Part of the question we will basically answer them by text, right? And so that's it. And let's kick it off. And Malte, it's your.
Thanks, Sam, for the introduction. And yeah, I'm super happy that we are having this event today, that we're hosting it together, Jina and Deepset, both from Berlin, both working on neural search, and both really sharing this open source spirit. And yeah, with that, welcome to the first talk tonight. The next 30 minutes, I will basically tell you something about question answering at scale with Haystack. I will try to give you an idea how to get more meaningful search results with question answering. And we will talk there about latest methods from research, some engineering tricks to actually make that work at scale, and how you can do that then open source with open source tooling with Haystack. And these three topics also pretty much describe my daily job and what I'm really passionate about. Open source, research, and engineering. I'm a co-founder of Deepset, small startup here from Berlin. And yeah, our mission is basically taking latest models, latest methods from research, applying a lot of engineering to them and make them work for the industry. And our absolute focus these days is building industrial neural search, and our core product there is Haystack. With Haystack, you can really get very granular results in your search. We are only talking here about text search. It's maybe an important point. And with Haystack, you can make it scalable. So scalable question answering model, that's what it's there for. And all of that we're doing with open source. And in the end, we earn our money with then some enterprise editions, which are useful for large organizations. We have actually clients from all around the industry, different domains, a lot of technical domains like Siemens or Airbus, but also many from financial background, like BaFin, for example. But yeah, they all have in common that they have huge piles of text data, and yeah, they want to make some sense out of that and use search for it. So when I talk about search, let's maybe make that a bit more clearer. Like what are we talking about? And I think it's best illustrated with web search. Everybody knows web search, Google. And if you think back, like maybe 5 years ago, it was mostly like keyword search. You were like connecting or collecting different keywords, and then went through the list, clicked to different sites, and then found your insight that you want. If you do the same thing today, things have changed quite a lot. First of all, your query is usually now in like natural language, or at least you can do that. So you can ask really, where's the Eiffel Tower? But then also in the results, you're not only having like a ranked list of documents, but you really also have granular answers directly to your question. So there's no need anymore to actually go to the website because you already found the answer that you were looking for. Well, that is all like pretty common, or pretty, you know that from web search. The enterprise world is still very different. If you want to build now something from like that yourself, that used to be very hard, and all these search engines relied on a lot of metrics that are very specific for web, like PageRank and so on. And the good news is that things are now changing, and you can pretty much build something like that by yourself. And let me maybe start with a quick demo. So what can you build really with open source tooling today, and with Haystack, with the open source framework that we have. So in this demo, we basically indexed a couple of documents, like financial documents from NVIDIA. And yeah, many of our clients come from financial industry and want to make some sense and want to dig into these reports, like annual reports, earning calls, and so on. So let's be one of these financial analysts and try to ask a few questions in natural language. So for example, one thing that I might be interested in is how high was revenue in 2019? And behind the scenes, we're now like querying into our index, different documents, and we already see here then highlighted actually what we were looking for, 11.72 billion US dollars. So let's maybe ask then something slightly more interpretable, I would say, more challenging. What were the main factors impacting actually our revenue? It's not really, I would say, like a typical factual question, but more something where we are asking for some more context, interpretation, where it needs to understand a bit semantics. And here we find, okay, for NVIDIA, main factors that impacted revenue are actually like infotainment modules, production drive platforms, so something for the automobile support, I think, and yeah, here development agreements with automotive companies. And of course, we can go on like that and maybe then ask, okay, how is the actual outlook for the future? And in all of these questions or like answers, you will see that there's actually not much of a keyword overlap. It's here, I think there's nothing mentioned like outlook. They basically talk about what they expect. They expect like cryptocurrency related revenue to be legible going forward. And of course, you can browse down, and that's how you can like basically orientate or navigate through a large corpus of text in a way smoother way. So that's what you can build pretty much with methods that are out there today that are open source. So let's have a look what is behind that. What are the core components? I would structure this talk today into 4 different parts. First, talking about language models, which are pretty much the backbone of these systems. Then about question answering more in general, and how you can use language models to do that. And then in the third part, how you can scale that. How can you really apply it into large document bases? Let's start with the language models. I guess most of you who are, have been in NLP or read anything about NLP in the last 2 years, you will be aware of BERT. It was everywhere. It was super hyped, and it really changed, I think, how people are doing NLP today. BERT is, I would say, the most popular language model out there, even still today. And it basically was pre-trained on some quite large corpus of raw text, Wikipedia and book corpus, with 2 particular tasks, a masked language model and a next sentence prediction. We don't need, I think, today to dive into details what that means. But the important thing is you can train it on just some text, like raw text, no annotations, no labels, just take some text, that's it. And then the core idea here is with transfer learning that you have then this pre-trained language model, which has some notion of textual understanding or like patterns that are in there at least, and then apply this model for different tasks, different downstream tasks. And in these tasks, you basically fine-tune the very last layers of the network, or add or exchange those final last layers. And with that, I think it pretty much has become a modern baseline model for a huge variety of NLP tasks. But because BERT was so successful, there are now a lot of other language models out there, and it's sometimes a bit tricky to keep the overview, I think. I will share the slides afterwards. If you're interested, maybe look up these guys here in detail. For today, I only would I think highlight a few of them here, which are particularly relevant for QA, and at least for our work, what we do, and we do QA. There's XLM Roberta, which is pretty interesting if you want to do cross-lingual or multilingual language modeling of QA. There's Roberta, which is one of our currently, I would say, favorite models, super robust, can apply it easily or adapt it easily to different domains. And it's basically a BERT variant that was trained on more data, more training time, and with a larger batch size. Something that's also quite interesting, and we see it later today in the talk, is MiniLM, a quite recent model, which is a bit smaller. It's a distilled model of BERT, more or less. This is interesting because it's faster, and that's for QA always an important factor. So how can we adapt these guys now for the task of question answering that we're interested in? First of all, what is question answering? If people talk about it, if you read papers, usually when they talk about question answering, they mean a specific variant of it, which is called extractive question answering. And this task is pretty much, you have your free-form question that you can formulate in natural language, and then you have one rather short text passage. And the challenge now is to find the answer within this text. So it must be somewhere in there. It must be one span, which is kind of connected. The task for the model is to find that answer. A few challenges with this kind of NLP problem. First of all, there is an interaction of text and question. So basically, you have here like some free dynamic input, and you have here also a second type of input. And only in the combination of both, lets you find the right answer, like the right prediction. And of course, there's like a huge set of potential predictions. It's not like in, let's say, classification or maybe NER, where you have a predefined list of a few classes. But really here, it can be any combination, any span that you find in this text snippet. And of course, you need some kind of contextual understanding to answer a few questions. Sometimes there's some information in the beginning that you need to keep in mind or in memory to find an answer in the end of the text. The currently, I would say, most popular approach out there is to train a model, which is also called reader model, that predicts the start and the end of such a span. And you take basically one of those language models that we saw on the previous slide, BERT, Roberta, some of those, and you fine-tune it on another small data set, a label which has labeled question-answer pairs that the model can learn from. Probably the most dominant or prominent example of such a data set is called SQuAD from Stanford, and pretty much has become the default, at least starting data set to train such models and evaluate those models. How does it now look from a model side? We have basically our question and the text. We feed both into our language model, in this case BERT. This model gives us some contextualized token embeddings, so one vector per token. And we feed that into our prediction head, which is particularly suited for the task of question answering. This prediction head gives us then the start and end position of the token, and we can align that back to our string space. And that's pretty much it. That's what happens behind the scenes. And if you think now, okay, what's happening in this question answering head? To be honest, not super much, not that much. It's pretty much a simple feed-forward neural network, which iterates over tokens, let's say, with these embeddings, and predicts logits, one for the start, one for the end. And it goes over that. In the end, you have basically one logit per token, and you then kind of look for the best combination. There are a few heuristics, post-processing steps involved, but in the end, you're basically looking for the highest start logit and the highest end logit, and that's what gives you the answer. So why is that now an interesting task? Why is it an interesting time to talk about question answering, to be in there, to apply it, to push the boundaries of that? You see here from like a chart from Papers with Code, how the performance on this SQuAD question answering data set has evolved over time in the more or less like last 2 years. And you really see that here there was like a bump. And this is basically when transfer learning happened, or like was basically enabled by BERT and the publication of BERT. And it really then became, the models really became feasible or applicable for industrial use cases. And that's really also what we observed when working in the industry, talking to clients. We saw that from one moment to the other, these question answering models were not only relevant from a research perspective anymore, but people said, yeah, well, these predictions make sense. I can use that. That helps me in my daily work. And this was a big moment for NLP and question answering. And since then, also research has really picked up on that. And if you look at recent conferences, there's a huge momentum in research, which again boosts this question answering, I would say, into different directions. One is actually improving accuracy or giving more meaningful answers. There are new models, new challenges, new types of QA out there, and it's a pretty active area of research. The second direction, of course, is always speed. Like these models are super heavy, big neural networks, and everything that helps us to make the predictions faster is super helpful in industry. Another stream looks as well on other languages. Traditionally, a lot of NLP work out there is looking for English and is modeling and evaluating only on English data sets. But I would say in the last 1-2 years, for QA, there has also been a lot of development on multilingual models, other data sets, and that's super interesting to see. There's not only a big momentum in research, but also actually a high demand from industry. And I think that both, there's like some dependency, right? Like if there's something interesting happening in research, people in industry want it. If there's a big demand in industry, also research starts looking more into that. And that's really what we observe currently in this area of question answering. The high demand from industry, from my perspective, is driven by a couple of factors. One of them is that there's a growing number of information workers. So many people really that spend hours and hours reading text and who are a bit annoyed of that. And they are annoyed of that because they are used to like the web search experience. And there they see, yeah, I can get my information way faster than I do maybe in my enterprise setting. And this gap, of course, caused then some demand, and people are asking in the IT departments, what can we do? Can't we improve that somehow? And they also become more creative and say, yeah, maybe there is something possible. And of course, there are many use cases beyond typical search. So many of our clients actually use it also for different use cases where you have always the same, let's say, standard set of questions. And for every incoming document or email or whatever, you basically want to ask those questions and get back the answers that you can then process after next subsequent steps in your process or in the Excel sheets or databases, whatever you like. And also in conversational AI, there's a growing interest in question answering to go beyond, let's say, classical intents. So that was really extractive question answering in 5 minutes, more or less. I could talk, of course, way more about that, and happy to answer questions. But let's now move to, I would say, for us, the most interesting, but also most challenging part of question answering, which is actually scaling it so that you can use it in production and in the industry. This is also called usually like open domain QA, and there you really want to find an answer in a large collection of documents. So now we don't have here like a single small passage, but thousands or millions of documents. And of course, the main challenges here is first of all speed. These transformer models, if we were just applying them natively, they would basically never end if they have like millions of documents that they need to process. So speed is a big thing here. How can we make it usable? A big challenge as well is that not only speed, but these models, they basically have a limited input length, which for these transformer models is usually quite small. And this also means that we need to chunk even a single document into multiple passages, multiple things that the model can process. And this is again like increasing decreasing the speed, increasing the time that we need for processing. And also we need then afterwards to aggregate all those predictions and how can we actually make sense that and do that in a meaningful way. The current, I would say, best practice out there is to use a pipeline that is called retriever-reader pipeline. And it basically works like this. You have a document store, some kind of database, which has all your documents. And you have a retriever model, which queries the documents from the document store. And it first gets like all these documents in there, and it spits out basically the top K, the most promising candidates. So basically reducing the size from, let's say, millions to a couple or dozens of documents. And those documents are then actually fed into your reader model, which is again like a bird or something like that, and can then in detail scan those passages, those documents, and find our answer. And with this idea, it's we get a pretty good speed up. So if you take a quite small data set here from natural questions, around 7,500 documents, without this retriever-based pipeline, that would actually take more than 3 hours per query. So like completely insane, even for such a small data set. With a retriever, we get something around 0.3 to 2 seconds. And this is then pretty much scales also to millions of documents, because this retriever is not very dependent on this number of documents. So let's have a look at those components in a bit more detail. What is the retriever doing, and what is basically the state of the art there? I already said the goal or the task of this retriever is to identify promising documents from a large collection. So I would say a classical information retrieval task. And if you look at the landscape of models that are out there, there's quite something happening, and there's a big, I would say, big shift happening. And let's have a look at 4 prominent methods that are out there. First of all, there's BM25. So that's pretty much old, established baseline, super common in the industry. And it was actually a tough to beat baseline, I would say, for the last decade. Like there were a lot of papers, a lot of attempts, but most of them that I saw were having a hard time to match this one and actually beat it. It's also what's implemented into Scene. So what's Elasticsearch is basically actually using behind the scenes, more or less. And it's based on bag of words. So really sparse representations of large documents. And with that, we get here around 60% of top 20 retrieval accuracy. So if we get the top 20 documents out of a large data set, in this case it's Wikipedia, with natural questions as a question data set. In these top 20 documents, in 60% of the cases, our target document is included. So then for these, we can, for these 60% of cases, we can actually find also an answer with the reader model. It gets slightly better if we now go to these newer methods, which are all based on dense embeddings, which is a slightly, I would say, paradigm shift that is happening out there. And I'm sure Han will talk a bit more about that in his talk. Let's just quickly go through them. I just want to give you the basic idea here today. And if you're interested, then please check out the papers. I've all linked them here and see what they're really doing then in detail. But the main idea here behind latent retrieval with inverse closed task is that you train 2 encoders, one for a question, one for the passage. So 2 networks, and these networks create embedding representations for both of them. And this paper was published, I think, last year, 2019, and they basically used a smart task here called inverse closed task, which basically takes a sentence, and the task for the model is to predict which is the context that goes around the sentence, which is a bit similar like the question answering or retrieval approach, where you have a query and you need to find a passage that matches or makes sense. Then there was Realm, which I think was published earlier this year from Google, and they actually do like training from scratch, something like BERT, like on the large data sets. And even in that early stage, in this pre-training of a language model, they actually include a retrieval step where the model basically needs to pick a document from a large collection that is useful in this pre-training task, which helps the model to fill in the blanks basically of this master language model. And that already boosted then performance later in for QA quite a lot. If you see here, like we came from 60%, we're now almost approaching 80%. That was actually a big leap. And that these three, they all happened within the last year. Let's now talk about the last one, dense pest retrieval, published by Facebook AI. Super nice paper, I can definitely recommend reading it. And there, the main idea is, again, having dual coders and training them. But there, one smart way of doing that is to use a special way of sampling negative examples. And this is pretty much now state of the art. And let's have a quick look now what is behind that. In this paper, dense pest retrieval for open domain QA, the main idea is you have a question, a passage, you feed both into individual BERT models, and these BERT models give you a final representation, and then you apply the dot product, which is your similarity metric. And why do we need two BERT models? Basically because the question and the passage usually have very different style of text. This is usually short, this is long. This is some kind of question, always from the syntax a bit different, and this can be any type of text, any type of passage that you're interested in. And that's why it makes more sense if you have two different encoders and they can differently embed these texts. So that's one thing, we have these dual encoders. Now, what is the smart part of this paper? It's basically how they sample and how they train. They take one question, one positive passage, so one that belongs to this question, and then n negative passages. And on these pairs or like these samples, they basically train the network using this dot product and minimizing then the loss on that. The cool thing now is what they do is this negative sampling, because they say, okay, let's have a batch size of 128. I have one question in there. Let's use the other 127 samples in our batch as negative examples. And with that, they can have a very efficient way of scaling it and really using all information that we have in this batch to train the model. Plus, one more thing that they do is then making it a bit harder. They say, okay, I also take one other negative example, and this is what I would get with BM25. Like if I do this query with BM25, the best ranked passage that doesn't include my answer, which is so negative. And with these hard negatives, they also boost performance quite a lot. In the end, they also then train models on multiple data sets, and that helps them even more to boost performance. What is cool now, the inference part, is you see here like two BERT models. Maybe you get already afraid, wow, okay, it's never hitting production if I have two BERT models there. But the good thing is that now you really need just to can pre-compute the embeddings for all those passages. You do that once, you index it to some database, for example, Face or Jina. There are also other ones out there, and these document stores or databases have quite efficient indices to actually store those embeddings and then compute similarity at inference time very, very fast. Inference, what you do is basically then having the question, you encode that, and then you get the k nearest neighbors from your index. That's pretty much it about the retriever for today. So let's quickly have a look at the reader then. As I think I'm running a bit out of time, I will go a bit faster through the section, but happy to answer, of course, questions then later. On the reader side, there's also a lot of research, a lot of stuff happening. I just have here like an overview of models that we are using a lot currently. And I mean, as you saw on an earlier slide, there was like a big boost in performance like last year, where it was like big jumps actually. Now I would say like these latest models in their base version, so like a rather small model, there's no super big difference. There is, I would say, from BERT base to others, there is. And for example, Roberta is a model that we use quite a lot. And there you really see also like this difference might seem small, but in production, users really feel it. And it's not always, I would say, also about these scores that are here measured on Squad. It's in the end also about what can you do with those models in reality. how easy can they adapt, how flexible are they, if they see out of domain data from different industries. And there, for example, I can highly recommend Roberta. We made pretty good experience with that. It's very flexible, easy to adapt to other domains. Maybe one other model that I would flag here is MiniLM. This is quite recent model. And here the interesting thing is that it has pretty much on par performance. It's as good as Roberta, better than BERT, and it's faster than both of them. So let's have a very quick look at that one. The idea is, well, the model is basically a distilled model. This means there was a bigger model before, and which is usually called a teacher model. And this MiniLM is a student that learns from that teacher model. And in that case, it's actually you learn from UniLM. And our target model, like the student, is quite a small model, like 33 million parameters, which is about a third of BERT. And they have a special technique of how they do this distillation. Some of you might have heard about DistillBERT. And here, in contrast, they do have a different objective in the end. They basically try to use the last attention layer, and the student must mimic this last attention layer. And if you're interested, in the paper they have a very nice explanation what that really means, what matrices they mimic, and what goes in the loss in the end. For industry and for practical usage, what is interesting, I already mentioned like performance. It's better than BERT base, so that's quite nice, while being faster. And that's actually, I think, the even more relevant part, because speed is really, I think, in the end what people need out there, and also where I see currently the biggest, most interesting stuff happening in research. And yeah, not too also often a big requirement. Memory, this model is smaller, only a third, so also the memory footprint is considerably smaller. Yeah, now you had like a deep dive, or like a overview at least of different research methods. So let's talk now a bit more practical. All of that you've seen here is now really, I would say, latest research. There's a big variety out there. Of course, there's code, but usually if you want to run this in production, it takes you like a week to find all the different components. And then if you want to switch from one model to the other, change the retriever, then you have a completely different code base. And this is really like the idea behind the haystack, that you don't have to do that. All these components are within the framework, and it's very easy to change them. So most of that should seem now a bit familiar. The document store is basically something like Elasticsearch or Face, where you index your documents. You have then like a retriever, where you have different options. For example, the dense passage retriever that you can initialize. You have then a reader, basically any model that is, for example, in Hugging Face transformers, and like in the model hub, or if you're familiar with our framework, Farm, anything that you trained there. You can then stick those together to a pipeline, or we call it Finder, and then ask this Finder questions and basically get your results. So from a code perspective, from a high level, it's quite easy, I would say, to get started and try it out. But what is also important to us then, if you like in the second, let's say the second week when you dive deeper, then I think actually that's really the power then of Haystack. That is really modular. You can extend it, you can modify these components, and you can make it work for your tech stack basically. So we have all these like readers, retrievers that I already showed. And of course, then it doesn't stop. We have like an API on top, a REST API that you can easily then integrate into your client applications, Dockers for deploying it, for scaling it. And of course, like also if you want to really apply it in industry, we often hear, okay, how can I adapt it to my domain? My corpus is very special. We have two options to do that. One is basically via user feedback. So if you have your system in production, users can give thumbs up, thumbs down, and the model can use this feedback then to adapt and learn over time. The second one is you have a dedicated labeling process where you have people basically answering question answers and annotating a few labels. The good thing here is that usually you don't need massive amounts of labels. Usually like 1 or 2 weeks of work are basically enough to get there a decent amount. If you're interested, yeah, check out Haystack on GitHub. We live open source. We're really passionate about it. If you like it, if you use it, open issues, ask us questions, contribute, and of course, leave us a GitHub star if you like it. That would be awesome. We like these interactions. They're super important to us. So let's wrap it up. For this talk today, what should be important to get away of it? First of all, transformers really enabled this extractive question answering that we saw. In industry, we mostly require the open domain QA, the scalable version of QA. And for this version of QA, for the scalability, retrievers are the core, and we really need those. And yeah, you can implement all of that yourself via Haystack. So get started, try it out, give us feedback. Of course, yeah, there's like a lot of interesting stuff happening in the future. I'm sure like when we talk in 1 year from now, new models have evolved, new retriever approaches, generative QA, like with GPT-3, which was recently released. There's interesting directions there. And of course, more like reasoning synthesis. So if you not only want to find a span, but combine knowledge from different locations of the text. Yeah, if you want to get in contact, yeah, check us out or follow us on LinkedIn, on Twitter, and very important, we are hiring. We're looking to grow our team. So if you think that one of these positions might suit you, please reach out to me. Yeah, we're looking forward, and it would be cool if you join us. Yeah, thanks. That's all.
Okay, thank you. Okay, thank you, Malte. So first of all, thanks for Malte for the fabulous talk. So basically, I just introduced myself a little bit. I'm Jen. So I'm today's moderator of today's webinar. So I'm working for Jina AI as an HR. So if you are interested in working with Jina, with us, feel free to send your resume or CV to Korea Jina AI. So now I will share my screen, and it's time for the Q&A session. So here comes the first question. So the first question is, can we use Haystack for semantic search of documents?
Yeah, absolutely. So I mean, it depends a bit like on what you mean with semantic search. But in the end, you have we see it in these 2 stages. Like first one would be retrieving relevant documents. So if you're only interested in a list of documents, you can pretty much use this retrieval step. So for example, dense path retrieval or Elasticsearch in the end, both would be options. What Haystack offers on top is then really going into these documents and finding there the granular text snippets answers that you're looking for.
All right, thank you. And the second one is current search algorithm feel primitive in comparison to the results from GPT-3. Could you say some words regarding the impact you see GPT-3 having on search?
Yeah, sure. So I mean, first of all, GPT-3 is super interesting. I think yeah, it's really a new direction for models, and it's impressive to see like how it does on different tasks and how it can just learn from very few samples and like extrapolate on that. So that's great. For search, I'm still like a bit skeptical. Yeah, I'm looking forward to see like how it really will work. I think it already shows some power or like some interesting features for example, query expansion. So if you, let's say you have one query going in, GPT-3 I think can easily like rephrase it so that you have more queries to shot, and then it's sometimes easier to find the meaningful snippets. On the other hand, the answer that GPT-3 gives is by no means, there's no way that it's correct. And this is for industry, I think, a big challenge. Like if GPT-3 generates an answer, you have no way of checking that. And while it's that might be okay for some toy applications, in industry, if you ask what was the revenue of NVIDIA 2019, you cannot rely on a generative model, I would say, in this stage. You would always need to ground it with some facts and then some real snippet in the text that in the document. And this is, I think, one challenge. And the second right now is how do you adapt it to really then a domain? If you ask it a question, now it can generate an answer, yes, based on the knowledge that is in the internet. And if you're interested in that type of data, that's cool. But if you're working in a certain industry, you have, let's say, your own technical documentation at an automotive company, I don't think that GPT-3 will be able to answer that.
All right, thank you, thank you. And the third question is, how do you handle search with BERT in long documents? For example, the technical reports with 10 to 100 size of pages, do you split them into independent chunks of 512 tokens maximum?
Yes, exactly. So that's basically what you do. You have these long documents, you split them up into passages, for example, of 512 tokens, usually also with some overlap, so that they are not cut it just in the middle of a sentence, but you have like a striding window. And yeah, you then basically query them individually, or not individually, but you have all of them indexed. You get then, let's say, top 10 of these passages out of your document store with a retriever, and those you then feed into BERT, and BERT scans through all of them and aggregates the answers across these passages.
Okay, here comes the last question, and then it's Hans' turn. Okay, so does the BERT-based QA model understand the concepts? For example, Berlin is a city. If not, how would something like that be achieved in combination with LM-based QA?
I think the wording understanding is always difficult. Like I would say, yeah, it has some notion of like that Berlin is a city, and it definitely sees this pattern and can extrapolate from that. And yeah, you can definitely has the notion that Berlin is a city, and if you ask some city-related question, it will pick up Berlin as a word. If that's really understanding, it's a philosophical question, I would say, and you can argue like if these language models, what they're actually doing, if they're understanding the text or if they do very, very efficient pattern matching. But yeah, they work, so they can definitely find those and interpret this semantics. Yeah.
Okay, thank you, Malte. So we will have another big Q&A session after Hans' talk. So you can just ask your questions here. Okay. So Han, it's your turn now.
All right. Yeah. So thank you everyone to join this webinar. So as Jens just said, so if you have any question regarding Malte's previous presentation, please also leave the questions there, and also like put a prefix like at Malte or at M, so that we know that this question is for Malte. And we will come back to those questions after my presentation. All right. Yeah. So hello everyone. My name is Han. So I'm the founder and CEO of Jina AI. So a little bit of introduction about myself. So Jina AI is a pretty new company. We just founded in February 2000. So basically this year, 2020. And before that, I was an engineer at Tencent AI Lab. So where I built the search infrastructure behind WeChat. So WeChat is a very popular social app in China. So inside that, there is a search engine. So it's a kind of like a mini box, right? You can search a lot of things inside WeChat. And so my team is responsible for building the search infrastructure behind this WeChat. And I'm also the part of the Tencent OSPO. OSPO is open source program office. And so basically I was like representing Tencent in some international open source initiatives or organizations such as Linux Foundation. So I do live in Germany for many years. I studied master and PhD in machine learning at TU Munich. And then I moved to Berlin, joined Zalando as a senior research scientist. So some of you might know my previous open source work on fashion and needs. So this is benchmark. This is like a standard machine learning benchmark data set I made when I work at Zalando. And So the other project I was doing is the bird as service. It's kind of like a network wrapper around the bird, so to make it bird really efficient in production. Right? And so I'm also part of the TSC member, so technical steering committee member of the MindSport, which is a universal deep learning framework from Huawei. And yeah, so let's go to the next page. So regarding our company, Jina AI, so we call ourselves as a neural research company. So Malte already introduced what neural research is, but if you never heard about neural research before, so basically in the academia, we call this neural information retrieval. So basically the idea is to use deep learning as kind of building block to rethink or rebuild the whole search engine, right? So the core algorithm is not based on symbolic search anymore, it's based on neural network. So this is so this kind of system is called neural search, neural information retrieval. All right, so we want to provide a cloud native neural search solution empowered by the state-of-the-art AI and deep learning. So our mission here is really to build an open source neural search ecosystem for business and developers. So this is super important. We are an open source software company, and our goal is really to make building such neural search engine really easy for any developers without any, let's say, professional backgrounds. And we aims to be our system is aimed to be very let's say highly scalable, high available, this kind of high performance metrics. So as I said, we are a very young company, but we have grown very quickly to become one of the most, let's say, high value AI cost company startups in the world. Right? So we are rapidly expanding our engineering team in Berlin and Beijing. So right now we have 11 employees from 5 different countries. That includes from Microsoft, from Google, and also Adobe. And by the end of Q3, we're expanding our team to 20. And at the end of this year, we are expecting 30 employees from all over the world. Yeah, so we have job openings, including AI engineers, front-end and back-end, Python, and especially the DevRel specialists. So we basically want to, as I said, we are open source company. So we really want to build a very good relationship with developers, with community to earn their trust and to build the neural search ecosystem together. So that's why we are building the DevRel team in Q3, starting Q3. So if you are interested in these roles, please send your resume to us. All right. Okay. So far so good. So now we're talking about the neural search. So the idea behind neural search is pretty, let's say, pretty straightforward. In the classic search, usually the input is basically keyword, right? So you type some tokens and then you search for the related document that somehow match your query, right? But for the neural search, our motivation is really to search all kinds of data, right? So that includes long text, long PDF. That includes images, short videos, sound, and so on, right? Source code and maps. Right? So, but the thing is that let's take a concrete example, right? So let's say you are the search engineer from a company, right? And you want to build from an e-commerce company, and you want to build a shop's look, this kind of application, right? So this is a very intuitive, straightforward application. So basically you search based on the looks of the clothes, right? So you want to search the similar clothes with the similar patterns or styles. And then you want to build a search engine that can enable this feature, right? Of course, you cannot use like a traditional Lucene or Solr to do that. Well, the most intuitive way, at least, is to use deep neural network, right, to build a shop's look applications. But before we start, let's just close your eyes and think about, so what would be your current solution, right? What would be your current solution? You probably will use TensorFlow or PyTorch, depending on which one is your favorite. And then you learn a little bit CNN convolution neural network, and then you learn a little bit Elastic, you learn a little bit MongoDB, this database, And then you try to use Python or Java to glue all the tech stack together, right? So in the end, you spend, let's say, 1 or 2 months and build a prototype, right? Which underneath the tech stack is spread all over the place, right? It's very hard to maintain. It's not very easy to scalable, and it's just a prototype, right? And so to follow on that thread, so let me show you one demo. This is a Jina Hello World, and see how Jina solves this problem. And to do that, we first go to the Jina dashboard. So this basically is our monitor or dashboard. So basically you can manage or check out the health status of the search instance. And I'm going to start the backend here. So now what it does is trying to download the 50,000 fashion images, right? So basically the data set that I just introduced. And it takes some time, so let's connect to the backend. Okay, so now it's connecting. So it shows, yeah, you see that there are some logs scrolling over the place, and here you can see different part of the search pipeline or indexing pipeline. So basically the first step is trying to store these 50,000 images, right? And then the next step is to query, right? So let's see how the flow look like, how the index flow looks like. So the index flow is pretty simple, right? So you have a gateway which basically receives the data from the outside, and then you input to an encode. So this is basically the encoder. It transforms your image into some kind of embedding using deep neural network, and then there is an indexer, right? So basically stores the vector information and also the meta information of the images, right? For example, the original pixel of the images, right? Okay, so here you can also see the QPS speed, and you can also, yeah, so yeah, it's just a prototype, you know, we don't have so many functionalities to show, but you get the idea, right? So you can also see their properties, and you can set up at here, right? So you can also set up the properties here. All right, so now here comes the result. So basically, as you can see here, this is a pretty intuitive result. So in the first column, you have the query, right? So this is the input of, this is like the keyword that you type into the search box, right? And then the remaining columns are the top K results, the most visually similar results that are retrieved from the database, right? And that's no surprise, right? This is what the shops look like, right? And you see there are some arrows here and there, but you know, it's just a hello world. Okay, so as you can see, as we were talking, so we basically see so it's very fast. As we were talking, just 1 minute thing, but let's see what is the code, what is the implementation behind this hello world, right? How do we build hello world from scratch, right? So we start from like importing this Python library called Jina Flow, right? Then we start with empty flow, and then we add a CNN encoding, and then we add a indexer, right? And so this basically corresponds to the 2 components in the flow visualization. And then we just say, okay, please index the docs, and that's it, right? And so compared to our previous solution, our current solution, which use Elastic or TensorFlow, PyTorch, and then use MongoDB, and so this solution will probably takes you just 5 minutes, right, to write this thing. Okay, so some people say, okay, so this is a pretty, let's say, a very toy example, so it doesn't do you know, a very fancy things such as parallelization, sharding, and so on. But adding parallelization and sharding is actually pretty simple in this case, right? So you just add parallel equals 3, shards equals 3, and that's it, right? And that's how you do the parallelization, and this flow immediately becomes a parallel flow with database that supports sharding, right? And You can also say, okay, so let's take an example of bird, using bird. You can also use a bird as an image, right? So you can include the Docker image which wraps the bird, and you can use the Docker image here. But also you can say, okay, so my local machine, my local laptop is not powerful enough, so let's put it remotely, right? So let's move it to remote. So you can just write down the the IP address here, and well, when you start the flow, it will automatically start the bird in a Docker container in the remote host, right? So this is very easy to use. You can also do some like a little bit more complicated flow, such as you compute two embeddings. One is via the traditional classic convolution neural network. The other is via the residual network, and do the parallel encoding. So it's basically these two components will compute the embedding in parallel simultaneously, and then you collect their results, you collect their embeddings, and do the concat. You do the concatenation, and finally do the indexing, right? And yeah, so let's say you don't want to use Python, or you say, okay, so it's I don't want to maintain the Python code because I'm trying to deploy this thing into the cloud or into production. So I don't want to change my code base so often. So what you can do is you either write a very small YAML file, right? So you just write that describes the flow, what the flow look like in the YAML file, right? It's basically the same, right? So you write encode uses and then parallel index uses whatever configuration that you have here, or you can also put Docker image here and then put the shards here, right? And if you think that YAML file is, you don't know YAML file, you are a JSON guy, so you don't like YAML, so that's fine. You can also do this interactively using the flow design, the kind of interactive dashboard to do the hello world implementation. Okay, so far so good. We have index flow built. What about query, right? So how do we, because as you can see in our hello world example, we have two phases, right? The first phase is about indexing 50,000 images, put that into the database, and do some embedding, put that into the database. And the second phase is to query, right? How do we query from the store data, right? So query is basically as simple as indexing, right? So what you do here is you basically expose your port to the outside. So that allows the other people to use REST API or gRPC protocol to access your flow, right? And then you do you do a little bit changing on the indexing part. You said, okay, so now the pulling strategy is you pulling from all the indexer, from all the shards, and then you reduce it by merging all. So basically, you can imagine when we store the data, right? It means the data can go either one of those shards, right? But when you try to retrieve those data, right, you have to call each shard whether you have this data or not, right? And some shards say, yeah, I have this data. Some shards say, oh, no, I don't have this, right? And then eventually you collect them all and then do the reduce. Basically, in this case, it's merging all the results, merging all the top K results from all the shards, right? And then return the final top result to the user. Yeah, so that's basically the query flow. So as you can see, one immediate implication of using Jina is to save developers time, right? So previously, as I said, you had to learn different technology stack using TensorFlow, probably spend a month on that, and then spend another month on Elasticsearch, and spend a half month on MongoDB, right? So, and but now when using Jina, the whole thing can probably done in just 5 minutes or half hour, right? So we save human time. So this is super precious and super important for startups. To get the first prototype, how to bootstrap from the first prototype is super important, right? And so that's actually one of the highlights from Jina. So what else Jina can provide? So Jina is actually aims to be a universal search engine. So it basically you can use it to build the search system that do the long or short text semantic search. You do the image to image search, video to video search, audio to audio search, and there are also some cloud native features, right? Like a scalable elastic workflow, sharding, containerization, and so on. Right? So in summary, so we basically can categorize the the features that we provide into two categories. Well, one is multi or cross-modality search. The other is about cloud native. Right? So in the end, we really aims to build Jina as a search AI in production. Right? So it aims to be universal, can handle all kinds of data. Right? It aims to be cloud native, supports containerization, microservice, and as this CSE DevOps, this kind of thing. And it saves you a lot of time to build a neural search engine from scratch. And it supports all kind of, let's say, very powerful AI models that you can use it in a very easy way or plug and play way. So here we show some demos like image search, QA search. Those are very like a typical search, semantic search use cases. And we have video search. So basically the input is a short video and the output, you get all the related short videos from Jina. Okay, so let's take a look at the second example. So the second example is built on top of Google Big Transfer. Right? So this Google Big Transfer model is released in June, right? And so basically in the weekend, I just spent one night in the weekend, and basically to migrate the Google Big Transfer into production using Jina, right? I mean, I don't want to go into the details of the code because it's basically the same pattern as Hello World, and I just want to show you. So basically, as a backend, we start the big transfer, right? And then we basically have this kind of Jina box as a kind of front-end playground. And then you can basically drag and drop your images and basically search for similar images. So notice that this result is purely on Google, Google Big Transfer. It's trained on ImageNet, right? It's pre-trained on ImageNet or whatever this public data set they have, right? So it's not trained on Pokédex or Pokemons, right? But still it gives a reasonable result. So that is also very good because Jina, this is how Jina helps you to quickly bootstrap the first prototype by using those pre-trained models, right? And so basically you can also do some very fancy things like you can also capture from the camera. Okay. Yeah, so basically you can also capture from the camera. I think you can just do this. No, okay, so, and then you do the search. Okay, so it doesn't work. How about camera, and then we do the photo, I capture the photo. Okay, anyway, so at least it captures my hair, right, my black hair. Yeah, so that's how it works, right? And yeah, that's how it works. Okay, so anyway, so this is the demo. The purpose I want to show this demo is that it's very easy to, let's say, bringing something from the academia or research field into production using Jina. And this is also one part of our design principles behind Jina to shorten the time between the research and AI in production. Okay, so the third time is I'm going to show our videos. I'm going to just, the third demo is about video, it's about long text search. Some people asked this question before. Let me optimize this a little bit. More to the optimized screen for sharing video clips. I'm going to just so Okay, so anyway, so basically we consider ourselves as one layer above the universal deep learning framework, right? So we have, when we talk about universal deep learning framework, we have TensorFlow, we have PyTorch, and you can use them to build a lot of things, but they are not optimized for search, right? And so we want to be the infrastructure for all kinds of neural search applications, right? So this is how we position ourselves. And the second way to describe Jina is that we provide a new design pattern, right? So if you think about in the programming language, there is a paradigm shift from the structured programming to object-oriented programming, and then recently we comes to the concurrency-oriented programming, right? In the search system, there is also such paradigm shift behind the design pattern of the search system. Right, so in the beginning, we have this catalog yellow page-like search, and then we comes to the elastic Lucene Solar, this kind of symbolic-based search. And nowadays, when people want to search multimedia contents from in their enterprise or as their individual needs, and we need a new design pattern to develop a such search system. And this is basically what Jina can provide you. And I don't know how many of you know the concept of first-class object. So basically, it means that this in the programming language, this means that this object supports all kinds of operations. Like you can pass it as a parameter. You can add, minus, do some kind of operations on the object. So for example, the integer and the float, they are always the first-class citizens in nearly all programming languages, right? So in Jina, we aim to provide the first-class support on AI models, right? So that's actually how it differs us from the other framework or search framework. Okay, so you can see that we already provide more than 100 executors in Jina. So basically this means more than 100 models in Jina, right? So this actually covers a lot of fields from NLP, from computer vision, from audio, and also from the traditional classic machine learning algorithm. But behind the scene, Jina has a very, let's say, concise, very lightweight tech stack, right? The main dependency is only basically these 5 dependencies are the only 5 dependencies that we have behind Jina, right? So we have protobuf, we have gRPC and ZeroMQ to handle all the network and microservice, this kind of thing, and we have NumPy as the computational infrastructure, and then finally we have this Tornado. We use async IO to do all the streaming and event handling. So this very lightweight tech stack allows us to run even on embedded device. Right? So right now you can even run a Jina on Raspberry Pi, and so this is also doable. Right? But behind the scene, we are actually very flexible. So we actually can go very low level up to the C or go long. And we can also go very high level to support all kinds of different deep learning framework, and also some cloud native frameworks such as Docker, Kubernetes, and so on. Okay, so this is basically how so we as a company, Jina AI as a company, we are not only provide Jina, this all kind of open source search framework as a one product, right? So as I said, we want to build the whole neural search ecosystem. So the core is actually only part of our product line. It's only a partial, one of our product. And on top of that, we also have our marketplace. This is called Jina Hub. And we have Echoes, which contains enterprise features such as logging, auditing, encryption, decryption, and so on. And finally, we have the cloud, which is a managed SaaS service. And so you can basically take a sneak peek on our dashboard, and this is basically a prototype of the cloud. Okay, so so the another thing I want to emphasize is how do we, a lot of people, when they first get in touch with Jina, so they think Jina is probably just a very small toolkit, and they can quickly, get their hands dirty. But the thing is that Jina is not a small framework. It's a pretty big project. As I said, we consider ourselves as a TensorFlow for search. So you can imagine the complexity behind Jina, and also the size of the project. It's much bigger than Birdeye surveys or Fashion Amnist, right? So my suggestion here is really to use Jina to build something small, and then try different features, and then scale it up, right? Or scale it out. And we are continuously optimizing the onboarding experience for developers. So we provide 0101s, a very, very cartoonish storybook for the beginners. And then we have a very comprehensive list of tutorials. We have very well structured documents. And in the future, we will also have our tech blog post. So the best way to get in touch or to get involved in Jina development, or to get help from us, is to post your questions in the issue board, or also interact with us in the Slack channel. So we have a relatively active Slack channel, so where we discuss hardcore engineering problem, like a pull request, this kind of thing. We also answer the community questions from time to time. Yeah. Okay, so that's pretty much it. And I will go to the QA session. I will move to the QA session. Yeah.
Okay, so Han, thank you. Thank you very much for your fabulous presentation. So basically our audience has a lot of questions about Jina and the company and the products. So, and in between we have some disturbing about the YouTube, but anyway, so let me share my screen. So can I share my screen?
Yeah.
Yes. All right. So basically here comes the question. So yeah, here's the first question is for Han. So if I have to index web page text in embeddings, and I have a few other ranking signals such as page rank, domain rank, etc., how do I combine those ranking factors with embedding of each web page to form a single embedding for each document or web page?
This is a very, very good question. So you basically notice that you basically point out that the performance or the quality of the search is really not only about embedding, right? It's about ranking, right? Because ranking is actually a very downstream, and it's very close to what end user experience, right? And so what I can say is that there are a lot of aggregation algorithms to combine different rankers result. And so one simple way is trying to take the average, but on the other hand, you can also build a simple, let's say, perceptron to take a weight average on top of all the rankers. Or you want to do something fancy to involve feedback loops from the users. You can also do learning to rank, right, as a last layer. But the real question is, when we have a search system, right, a neural search system that has a lot of components, can be tuned, can be adapted, how do we want to train such search system, right? Do we want to just fix all the upstream component and just train the ranker? Or do we want to, let's say, train the search system end-to-endly, right? Like we do in the neural network, right? And so those are the questions that actually depends on the use case, depends on the also the academia progressing on this kind of training algorithm, learning paradigm, and yeah. So this is my question to the this is my answer to that question. Yeah.
Thank you. And the next question is, how does Jina scale to a few billion document search?
Yeah, so basically in Jina, we already, as the first step, we built Jina as a cloud native system. So that means we are always taking into consider the scalability when trying to design some components, right? And Jina, if you use Jina, you realize that scale Jina out is actually no problem at all. So you can basically easily change the number of parallelization, and you can put different microservice. We call this part. You can put part in remote or in a very distributed way. So scaling out is never a problem for Jina. Regarding the scaling up, right? So we try to make each component or each microservice or each part as high performance as possible. So here we basically optimize our code. We try to write some, let's say, computational demanding code using low-level language, try to migrate some very computational intensive code onto GPU. And so basically this is always part of our consideration. Right? Yeah. And it is our continuous effort on scaling things.
All right, thank you. And the next question is, how does Haystack compare with Jina AI? This is a torture your souls question, I think.
I can go first, maybe, Han. Yes, from my perspective, I think Jina is the perfect tool if you want to do like a search on various types of documents. So we saw in the demos that you showed, Han, images, videos, all these. That's nothing that you can do with Haystack, and that's not in our focus. So we are not aiming for like all types of documents. We only aim for text, but they go very deep. So our specialty is finding, I would say, like very granular insights, very granular search results, high quality search results for text data. And that's what we want to master.
All right.
Yeah. So basically, I think Haystack and Jina AI, we focus on different, let's say, applications domain, right? So Jina AI, Jina basically, the framework Jina is trying to be as universal as possible and trying to solve cross-domain and cross-modality and multi-modality problems, search problems. So this is not only includes text, but also includes video, image, 3D models, source code, and so on, right? And so this is a difference.
Yeah, basically you are not the competitors in the whole industry. Yeah.
No, not at all. I think also like from our perspective, basically we will see Jina probably soon in Haystack as a document store, so that you can basically have Haystack on top. So that's how I think about it. If you want to have deeper insights in text, then it's Haystack. But if you want to really have fast retrieval, billions of documents, and using fast retrieval with embeddings, then I think Jina is a perfect solution, and that's how we can combine both together.
Mm-hmm. Okay, thank you. And the next question is also for Han. So is dense passage retrieval based on transformer models? Why and why not?
Yes, it is based on a transformer. Let's say you can use transformer model to do the embedding part. But regarding the retrieval, I'm not sure what you are asking.
Maybe it's
retrieval. Yeah, it's probably for Haystack.
Yeah, I think so. Like, I think I was like mentioning the dense pass retrieval, like this paper from Facebook and the method there. And I don't know if that's the question is referring to that, but I can imagine. In that case, yeah, it's based on transformer models. So they're using two BERT models, like two encoders, one for the query and a different one for the passage.
Okay. Yeah. And this one is for Han. So is the video of long document search available somewhere?
Yes, it's available on YouTube. Yeah.
All right.
So you can go to our YouTube channel. So just type webinar.jina.ai, and then you can go to the live, the live streaming of the talk, and then you will find our channels there. Yeah. Mm-hmm. So basically, we will from time to time put some demos, put some tutorials on our YouTube channel. Yeah.
Mm-hmm. So you can find our officially YouTube channel, or you can also subscribe our channel, and then if there's any new demos, so you can see that, right? Yes. Yeah, and this is the last one for Gina. So how should we understand Gina in the context of question answering? Is this some sort of dense retriever that is easier to use than haystacks?
No, so basically, if you think about the haystack is basically a solution framework for reading comprehension. So inside that is actually has a, let's say, it has a very sophisticated algorithm, a deep neural network to compute the similarity and to let's say to compute the similarity between the question and answer, right? And so these models are optimized for QA pairs, right? So they understand, yeah, what is the question and how is it related to the what is the answer and how is it related to the question, right? But the Gina, on the other hand, does not make this assumption, right? So basically, you can think of, so we basically consider the similarity in a different way. And so it's not like a pair. It could be just like just like a embedding-based similarity, just like which vector is more close to that one, right? We don't take the semantic behind the question and answer pair into consideration because we are building something more universal, right? So it could be image, it could be videos. So this is actually what we see from our perspective. So maybe Malte can also give some hints on these questions.
Yeah, so I think it's like a different approaches. So the one is basically comparing or like creating independent embeddings. So you can independently index the passages or documents, and then at query time, you can just use those and combine them, have a similarity metric on those. And that's, I think, what Gina is doing in a super efficient way. And for the QA setting, or in the context of QA setting, this is what we would call a retrieval. So like finding they are the right documents. And then we go on from there, like, and apply the reader on top to really go in details. And as Hannes has said, there's like another step, like another model, which goes into more detail and reads the text and tries to find the individual span. And for that, they really need to the interaction of question and passage. And this is why it's complex, or like why it's taking more compute.
All right. Yeah. Thank you. Thanks for the part. Okay, here's comes some questions for Malte. So how do we store feature vectors for training phase?
So I suppose you mean like for indexing in phase. So this, I would say, so basically phases could be an alternative, or is an alternative to Gina, but it's way more, I would say, lightweight, and it's not so sophisticated for scaling in the cloud. But it's a lightweight variant where you can index embeddings. And yeah, so from Haystack, for example, you can basically create then embeddings using an embedding model, for example, the dense passage retriever that I just talked about. And you would then have let's say, a matrix of embeddings, and you index those into a phase. And this is a quite simple call, I would say. And I think we will post probably a tutorial about this next week, and have it there. Yeah.
Okay, all right. I think here comes the last questions. So it's also for both of you, I think. So how Haystack or Gina could work with structured data like dgraph.io database?
I can go first. Well, we'll go first.
Yeah, structured data. Let's say, to be honest, Gina's main focus is not on structured data, because there are already a lot of packages, including Apache Solr, can solve structured data in a very good way. But let's say in some field of the structured data, there are some like natural language or images, and so I can imagine we can, let's say, combine the Elasticsearch and also Gina together to solve this kind of mixed structured structure and unstructured data in some way. Yeah.
Yeah, for Haystack, I would say it's quite similar. So it's definitely not the focus of Haystack. It's not, I would say, the most common use case for this type of question answering. I would say it depends on a bit like on how you want to work with the structured data. I could imagine that there are ways and like useful ways, for example, to use it in the retrieval step. So we had some cases where you have text data, but you also have some metadata on top of that. And of course, you can use that metadata to improve the retrieval. So, for example, you can, like in the previous question, there was like ranking or combining different similarity metrics. You could, for example, say, okay, I take my in the retrieval step, I take my embedding similarity, but I also consider filtering for certain attributes or how close a certain metric value is in my query. So we can combine that to find relevant documents. Then in the question answering step itself, I don't see it right now, but I think there's also some research around that you can use knowledge graphs and basically combine them, hop around these knowledge graphs to synthesize questions. But this, I would say, is still in the early stage and not part of Haystack also.
Okay, thank you. So basically, that's the most important questions that the attendants ask. So I will stop sharing the screen. Yeah. So yeah.
All right,
We
cool.
are about the time, yeah. So 9 p.m. Yeah. So that's cool. Very nice. So then thank everybody for attending, for joining this webinar. So I hope you get something. And make sure to check out our GitHub repository, Haystack, and also Jina AI, and give it a star and try to use it and share it with your friend or social network. And so your endorsement is really appreciated from our perspective. Yeah.
Yeah, also from my side, big thank you. Was a pleasure, was really nice. And yeah, hope to see you guys around, hear something, get feedback, and enjoy the rest of the night.
Okay, thank you guys. Thank you for attending this webinar. If you have further questions, just feel free to reach out our website or send us an email. If you would like to join us, please send your CV or resume to korea@jina.ai. So yeah, thank you and good night.